Welcome back. This is chapter 15 on stars, and this part 4 video is on patterns among stars. In this video, we're going to look at giants, supergiants, and white dwarfs. This picture shows a size comparison of the ranges of sizes that stars can be. Let's start over here on the left with this orange thing. This shows the size of the star Betelgeuse. Betelgeuse is one of the largest supergiant stars, and you can see it's an M2 class 1 star. Now, let's just think about what that means. M means it's one of the cooler stars. It's a red star. The Roman numeral 1 means it's luminosity class 1. It's a supergiant. And being a cool star, its surface is about 3,800 Kelvin. It's about 120,000 times brighter than the sun. So we say 120,000 solar luminosities. And look at its size, 950 solar radii. So it's almost 1,000 times larger in diameter than our sun. Now you compare that over here to this orange star, not a supergiant, merely a giant star. It's Aldebaran. It is the what's known as the red eye of the bull, Taurus. It is a K53 star. So K means it's a little bit warmer than an M star, so 4,500 Kelvin. The Roman numeral 3 means it's a giant star, 350 times brighter than the sun, and 44 solar radii, so 44 times the diameter of the sun. And then this tiny dot right here, let's zoom in 100 times, and here we have the sun. So you can see the sun is much smaller than those giants and supergiants. And here, the sun is a G25 star at 5,800 Kelvin. Of course, by definition, it's one solar luminosity in brightness, and by definition, it's one solar radius in size. But then you go much, much smaller. Look at this dot right here, Procyon b, which is a white dwarf. And you can see also for comparison the Earth. So white dwarfs are roughly the size of planet Earth. So in this chart, you can see the full spectrum of ranges of sizes of stars going from the very large, a supergiant, to a very small, which is a white dwarf. In this video, we're looking at stars that are off the main sequence. So remember, that diagonal strip of stars on the Hertzsprung-Russell diagram is called the main sequence. 90% of stars are on that main sequence. But we're looking today at stars off the main sequence. Stellar properties depend on both the mass and the age. Stars that have finished fusing hydrogen into helium in their cores are no longer on the main sequence. So as they get older, they will leave the main sequence. All stars become larger and redder after exhausting their hydrogen cores, and they become giants and supergiants. And in chapter 17, we will look at the specific processes that go on to make stars become giants or supergiants. But for now, in chapter 15, we'll just say that after they're done fusing hydrogen to helium in their cores, that's when they leave the main sequence. They become either giants or supergiants. Most stars end up small and white after fusion has ceased. So most stars will end up being white dwarfs. Let's do a quick review, some questions. Of these stars on the Hertzsprung-Russell diagram, which star is most like our sun? And so we can see B. I've actually put circle B right next to the sun, right over the sun. And let's think, why do I say it's most like the sun? Well, it's on the main sequence, and it's about the temperature of the sun. So we look down at G, about 6,000, 5,800 Kelvin. So any star along this vertical line is going to be the temperature of the sun. It's about the brightness of the sun. So there's one solar luminosity. So star B lines up perfectly with being like the sun. Which of these stars will have changed the least 10 billion years from now? All right. So let's think about what that green lettering shows. the lifetime of the stars. So these stars around where A is, these very hot, high mass main sequence stars, they only live for 10 to the 7th years. I mean, they're only on the main sequence for 10 to the 7th years, or 10 million years. So it's 10 billion years from now, it will have changed immensely. It would have left the main sequence and come over here, maybe be a red or orange supergiant. Star B changes, well, its lifetime is about 10 to the 10th years, so 10 billion years. So any star there will be, at the very least, on its way off the main sequence. If you think about a star like our sun, which is already 5 billion years old, it's only got another 5 billion years left. So any star that will only live for 10 billion years will be on its way off, and maybe already off being a giant. These stars, let's look at D. These giant stars, I haven't taught too much on this or anything yet in these videos, but they don't last as giant stars 10 billion years. So this giant star would have eventually faded down to become a white dwarf. But these C stars, there you can see in the green, I know it's kind of small, but lifetime 10 to the 11th years, which is 100 billion years. And down towards the very end where C is, that's as much as 1 trillion years. And so chances are a star that lives for 1 trillion years isn't going to change much in 10 billion years. It's possible that it could, meaning, well, no, I'm going to back out of that right now. I was about to say if it's been around for close to the end of its life, but remember, as far as we know, the universe, the galaxy, hasn't been around that long. So any star that's down here has plenty of time on the main sequence left to go. So C. Which of these stars can be no more than 10 million years old? And let's look back at A, stars above where it says lifetime of 10 million years. Well, the fact, if it's still there on the main sequence, it can't be more than 10 million years old, or else it would have gone over to be a giant already. So A. I want to now talk about variable stars. Any star that varies significantly in brightness with time is called a variable star. Some stars vary in brightness because they cannot achieve a proper balance between the power welling up from the core and the power radiated from the surface. Such a star alternately expands and contracts, varying in brightness as it tries to find a balance. So think about like an accordion. It'll build up all this power on the inside, it'll grow, and eventually it lets loose the brightness and then it shrinks back down. Then the power starts to grow up inside again, and it goes in a cycle. So here is the brightness versus time graph of a variable star. The light curve of this star shows its brightness alternately rises and falls over a 50-day period. There are different kinds of variable stars. The brightest ones are called Cepheid variable stars, and that's just because the first one of its type was discovered in the constellation Cepheus. Most variable stars inhabit an instability strip on the HR diagram, so you can see it right there. By the way, Polaris is one such variable star. And the most luminous ones are known as Cepheid variables. Let's now look at clusters of stars. There are two main kinds of clusters, open clusters and globular clusters, and you can see examples of them. And just looking at this picture, I want to point out that open clusters tend to be less packed together than globular clusters. An open cluster is usually a few thousand loosely packed stars. So they are all gravitationally bound to each other. None of these stars and clusters are actually touching, but they're loosely bound, kind of in orbit around their common center of mass. The Pleiades, otherwise known as Subaru, is an example of an open cluster. And that's a constellation that we see during the spring semester. And down at the right, you can see I've got the symbol for Subaru. and it's actually the symbol is loosely based on the pattern in the sky. A globular cluster is much more tightly packed together, up to 1,000,000 or more stars in a dense ball bound together by gravity. And this one, M13, prominent in the autumn sky in the constellation Hercules, is an example of a globular cluster. Clusters are important for astronomy because they help us measure the age of the galaxy. At the very least, we can measure the age of the star cluster itself by examining all the stars in it. The idea is that in a cluster, our understanding of star formation is that all of the stars formed from the same cloud of gas at roughly the same time, within a few million years of each other. And we will talk in chapter 16 more about the birth of stars. But for right now, think a cluster of stars is a population of stars that were all formed roughly the same time, and they're near each other, so they're roughly the same distance away from us. Now, if you think about a population of stars, the first ones to die out are the massive blue ones up here on the main sequence. Those are the ones that have a lifetime of 10 to the 7th years. As time goes on, then after the O stars have died out, then the B stars, then the A stars, then the G's, the K's, and eventually the M's. And when I say die out, that means that they leave the main sequence, so they've finished fusing hydrogen to helium, and they make their way over to the giant and supergiant area, and eventually most of them will become white dwarfs. But the point is, as more time goes by, they start leaving the main sequence, they start peeling off from the upper left. We can tell the age of a cluster by looking at how far up the main sequence do those stars go. If they stop right here where my pointer is, then that means it's a fairly young cluster. They still have those stars that don't live long. But what if all of this were blank in the upper left hand, and so nothing existed here in the cluster, but there was plenty from where my pointer is on down? Well, that means that stars that live about 10 to the 9th years or 1 billion years, they have all died away. But the stars that live more than 1 billion years, they haven't died off yet. And so if the main sequence, if a cluster shows stars on the main sequence that go up from the lower right all the way up here and then just stop right here where my pointer is, that tells us that that cluster has lived about 1 billion years. The Pleiades cluster, otherwise known as Subaru, now has no stars with life expectancy less than around 100 million years. So these are some data points. Every one of these blue triangles represents stars. And so here they are right there. And you'll notice above where my pointer is, there are no other stars up the main sequence. So this is what's called the main sequence turnoff point. And that tells us, since it corresponds to an age of about 100 million years, that tells us how old the Pleiades cluster is. So again, it's called the main sequence turnoff point of a cluster, tells its age. Now this chart here gets a little busy. They're putting data from 4 different clusters onto one chart. But you can see, for example, the blue triangles or the cyan colored triangles of the Pleiades that I already mentioned. But let's compare it with the purple diamonds, the H Chi Persei cluster. And what this picture is not showing is that purple diamonds go all the way down the main sequence. The illustrator of the chart wanted to leave it off to avoid too much clutter. So what you have to imagine is that there are purple diamonds all the way up the main sequence, and then it just kind of stops, although there's one right here. But for the most part, they see that there aren't too many stars, or it mostly stops right here. That's the main sequence turnoff point. What we're looking at is a very young cluster by astronomical standards, and they estimate it to be 14 million years old. Now contrast that with these tan colored squares, And these correspond to the cluster NGC 188. And there are no O stars or B stars or A stars, and it gets into the F stars. This is about where the turnoff point is. So because there are no O stars and B stars and not too many A stars, they can discern that this is a very old cluster. In fact, they estimate based on the stars that are there on the main sequence and the stars that are not there, that it's about 7 billion years old, so a very old cluster. To determine accurate ages of stars and of clusters, we compare models of stellar evolution to the cluster data. So models of stellar evolution gets into how do we know what those lifetimes are, the green writing on the HR diagram to begin with. And so that goes back to computer modeling and simulations based on that we have a big ball of gas made of hydrogen, helium, different nuclear processes, gravitational processes are going on inside them. And so we're able to use computer simulations to tell how old these different stars, how far along they get, how much time it takes before they leave the main sequence. Detailed modeling of the oldest globular clusters reveals that they are about 13 billion years old. And so as we think about how old is the galaxy, how old is the universe, one thing we can do to estimate that is look for where are the oldest clusters. And we don't find clusters older than 13 billion years old. In such a large galaxy, in such a large universe, if the universe were much older, let's say the universe were 1 trillion years old, we would expect to see many clusters with ages of hundreds of billions of years, but we don't find any. We seem to see this limit right about an age of 13 billion years old. So that's part of how we assess the age of the universe. That is the end of Chapter 15, Part 4. Have a great day.